John was talking about the process in which a smart contract is executed. So I'm going to go a little bit more in depth on that, and I'm going to just show you a small example of a smart contract. We're going to just follow step by step what it does. A bit higher. Okay, just on this. The contract consists of a storage which is on the chain. So this is publicly available, and it's all the information that is available to the smart contract. So you have the code and you have the storage, and that's what is staying permanently on the chain. In our example smart contract, we're just going to use an integer for our storage. It's going to be a very simple smart contract to increment an integer or something like this. When someone makes a transaction to the smart contract, they will be sending, it's like when you make a wire transfer to your landowner or something like this, and you want to pay your rent, and you put as a reference your name or something like this. The parameter is that reference. So we're going to be passing this alongside with some money. For the execution of the smart contract, it doesn't actually need money. We just need to pay for the transfer fees, basically, for executing the smart contracts and paying for the transfer of that data, which is in the parameter. The contract will return a list of operations and an updated storage, which means that it looks like this. So we have a parameter which comes in, which is sent when the user just makes a transfer with an annotation like this. And the behavior of the smart contract will read the storage, produce a new storage, and possibly produce some operations. The operations are just outgoing transfers. So for example, you could imagine a smart contract which, when you pay for your rent, it would automatically ventilate the money by sending some of it to this organization and some of that to the taxes and something like this. So let's backtrack a little bit and look at the individual components in detail. So the storage, as we were saying, is just an integer. And the message that you can attach, it's not just a free-form thing where you can write the wrong message or something like this when you're making a transfer for paying a rent or something like this. You put the wrong name and then it's a hassle to sort out. In this case, the parameter, we said that it can be three possible things. We can ask it to reset. So it will reset our counter to 0. We can ask it to increment, and we attach a value of how much we want to increment, or we can ask it to decrement, and we attach a second value to indicate how much we want to decrement. So it would look, for example, like increment 3, and this would just increment the value of the counter by 3. The results that we're going to return is, as I said, a list of operations. In this case, for this contract, it's just like a simple counter. It does not manage any funds or anything like this. So the list of operations we will return is always empty. And we return an updated storage. So this is our results type, which we just produce at the end of our contract. And now we have the body of the actual program itself, which is automatically executed whenever someone sends funds, usually 0 in this case, no funds, and a message to that smart contract. So So what we will do is we will declare our main function here, and we will take two parameters, or two function parameters. The first one is the action, the parameter here, and the second one is the storage. So we take action, which is a parameter, and store, which is a storage, and we will return, so this is the type of what we return, the results. So for those of you who are familiar with JavaScript, we have here a very JavaScript-like syntax, but with a few additions. One thing is that we have type annotations. So here we say that this is a parameter and this is a storage, and we just annotate that this pair of two things, this list of two elements, is a parameter and a storage. And we also annotate the result type. Another main difference is we sort of have something that is a bit like enums. So we have things where we can have a list of possibilities. A parameter can be increment, decrement, or reset. And in the case of increment or decrement, you have an integer attached to it. And when we have a value like this, what we can do is that we can match on it, which means that we're going to look, if it's an increment, then with the value of the increment, we're going to do this. If it's a decrement, we're going to do that. And if it's a reset, we're going to do that. So this is basically like a switch statement, or or an if then else on all the possible cases, but there are some additional benefits, as John was mentioning earlier. We care about security and avoiding bugs and things like this. You don't want to have a case missing, you don't want to have forgotten the resets, or you don't want to have an extra case for something like cancel or something like this, which is not a possible thing, because it's probably a sign that you have a bug somewhere. So LIGO, the compiler, will check that, given that it knows that action is a parameter, it knows that the three possible values are these three. And when we do match action with these possible cases, it will check that we have exhaustively gone through all the possibilities. We're not missing one, and we don't have one too many. So this is part of the features which allow us to avoid bugs, basically. So let's look at the body of this function. So this function main, we're taking the parameter and the storage, here both go in, and we're gonna return a new storage and some operations. What we return is, therefore, the list of operations, and it's just an empty list. So here we just have an empty list. Because, as I said, we're not managing funds, so we're not just gonna transfer any funds to any other contract or anything like this. And for the second value, the new storage, what we're going to do is we're gonna look at our action, which could be increment, decrement, or reset. If it's increments, the increment is supposed to have an int attached to it. So we're gonna get that int, and we're gonna return the initial storage plus that value. If it's decrement, we're gonna return the initial storage minus that value, and if it's resets, we don't need the initial storage, we just return 0. And that is all that we need to have for having our contract. So I heard someone earlier was talking about keeping track on the blockchain of things which are happening in the real world, like keeping track of transactions that are happening in the real world. You have a bunch of dollars that are being moved between accounts and things like this, and you want to just have some traceability of what happens to them. This is typically a smart contract which is only tracking information and does not handle funds on the blockchain. The only payments that are made is payment for paying for the operational costs, basically just paying for the storage, paying for the transfer of the data, which is transferred to, as John was saying, all the nodes who participate in the blockchain, and paying for the processor time for executing that contract. So, yeah, so that's about it for this contract. If I'm not mistaken, this afternoon later, there will be bigger example with how to deploy this and how to interact with it using Taquito.
Yeah, the Taquito workshop has deployment, right? Yeah, cool.
How are we on time?
It is now 13:02.
So I think that's about the end of this session?
I think so.
Yeah. Okay, are there any questions? I have to wait a bit. Excellent, it means that I did a great job at explaining.
I have a question.
One question.
Yeah.
Sorry, you know how in Solidity they have like emits?
Sorry, say that again?
You know how in Solidity there are emits? You emit messages.
Yeah.
Is there similar in LIGO?
Yes, so the operations here would contain basically messages that you emit to other contracts, basically.
I have a question as well. In terms of the storage, why are we storing a count? I mean, what is the storage usage basically?
So this is a very simple smart contract, which when you roll is to keep track of an integer that you can
Oh, so
modify.
the storage can be anything we want.
But the storage can be anything, yeah. At the top where we write type storage equals int, if you're building, for example, an NFT, your storage would be a big map, as John had mentioned earlier, so like a just big associative table from accounts to the amount of NFT that they have or something like this. And so you would just have a big map here, which would be mapping, for example, account addresses to some metadata, strings or whatever. So, any other questions?
Actually, I also have another question, sorry. Concerning the list of operations, so basically the contract returns the list of operations, but how are they then executed?
Okay, so,
built in?
yeah, so I will just go back to, what's the full screen one?
Function evidence.
Not made for people with using one hand. So, yes, you were asking
Yeah.
about how it is executed. So I'm sure
What
John
is the
mentioned
question?
something about this. Anyway, sorry, just can't find the slide. So when in Solidity, what happens is that you can call another contract. It will execute while you're running, and it will return to you the return value that it has.
Yeah.
The problem with that is if you call another contract, which calls another contract, which at some point calls you back, it will call you while you're mid-execution, basically. And you might have your storage in a slightly unstable state that you're not thinking that you could be executing when you're in this sort of intermediate state where you have half modified something but not everything. So in Tezos, what we do is that you finish the execution of your contract, and then the list of operations is executed one by one. So if you made a call to another contract, it will be called afterwards. And what it can do is it can call you back by returning a call back to you afterwards. So you execute your contracts, then the callees are executed, and if they want, they can, after the execution, schedule another execution. It's all executed in one block, and if one of them fails, everything fails, and it's just all cancelled, which is useful for avoiding some bugs, but also means that you can find your money deadlocked in some states. If you, for example, are trying to transfer money to a contract which fails, then you can't execute the operation. And if this is the only thing that your contract can do at this point in time, then you're blocked. So you have to always be careful to allow for the possibility of doing something else than calling other contracts to unlock you.
Thank you very much.
All right. Still another question? Did this spur some inspiration or topics that you want to discuss? No? Oh, good. Well, thank you.